Hello, everyone. So, uh, yep, let me share the entire screen and let us go to the mind map. Let me also parallelly check whether on my mobile I'm going to check on whether it's working well on YouTube Live or not.
Become an industry-oriented host.
Yep, seems like day 5 is live. All right, so let us proceed further. We are now going to quickly do a recap on the mind map of whatever we have discussed, and then we shall proceed further. Okay, I've seen a few questions about quiz questions. Where are the answers? Yeah, answers are pretty simple. You can just do a Google search and you shall find that. And let's proceed further. CRISP DM stands for Cross Industry Standard Process for Data Mining, in which we discussed about understanding the business problem and recording the objectives and constraints. It is recommended to write the objectives and constraints using 2 to 3 words. If you cannot, that's fine. But to the extent possible, try because it is recommended. It is also recommended to use the optimization terms minimize or maximize. Again, it is recommended. And then you have project charter. Once you understand the business problem, you proceed further with data collection, wherein you have various data types. You have primary data sources, secondary data sources. You first go after secondary data sources. And if you don't have the data here, then you go after primary data sources. Then we have data cleansing or preparation. These 3 steps, A, B, and C, cannot be delineated. They are overlapping. Once you have the cleansed data, you proceed further with data mining. But even before we get started with the machine learning algorithms, we will discuss about mathematical foundations, but then we discussed already about model evaluation techniques. We discussed about how to split the data into training, validation, and test, how to compare the training data, training error and testing error, model accuracy measures, error functions. What is the difference between error function, cost function, and loss function? We have discussed about all of these. And then we ventured into mathematical foundations. As part of mathematical foundations, while of course we have many things, we would be discussing about data optimization. And within data optimization, we shall discuss about only a few things, okay, not complete mathematical foundations as we deliver as part of our 80 hours training, but whatever is needed for us to understand the concepts, we shall discuss those. And here we go, mathematical foundations. We will discuss about optimization basics, derivatives, within which we'll discuss about minima, maxima, gradient descent optimization techniques, so on and so forth. Yesterday we discussed that. Let me select this. We discussed that. Whenever you have a business problem, you translate that into mathematical equation. Mathematical equation. And when you have this mathematical equation, you proceed further with that. And one more thing that we have to discuss is, or we discuss rather, is that rate of change is called as derivative. Rate of change or derivative is also called as gradient. Gradient is also called as slope. Slope or rate of change or derivative or gradient all mean the same. And you have an equation. And when you change the x value, okay, from one value to another, then what is the rate at which y value changes? This is called as gradient or slope. Slope could be like this, slope could be positive, etc. To understand better, let's proceed further and understand about a few of the finer nuances. Okay, so this is not needed now. If you change something along x-axis, what is the rate at which the values along the y-axis change? Gives you slope. So for the change that we do in x, what is the change in y? For example, if you change the x by 15 units, y is changing by 24 units. This is called as slope. If you have a single point, that means there is no change along x-axis and there is no change along y-axis. That means if you have a single point, the derivative of a single point or a single number is undefined. You don't know. You can also sometimes say it is zero. Okay, but then usually what you do is if there is a single point, you try to zoom so that it appears as if it's a small region like that. And instead of taking one point, take a small region around that point, and then you try to find the rate of change. That is what people do. Okay. A line connecting 2 points, x, y, and this, can be considered as a tangent if it touches only exactly one point. So you start from here. This is line A, say this is line B, say that you have line C. If it exactly touches a point, then this line is called as a tangent. And this is a formula for slope. If this point is x2 comma y2, and if this point is x1 comma y1, then the slope is given as y2 minus y1 divided by x2 minus x1. This is slope. y2 minus y1 by x2 minus x1 is slope. Rate of change along y-axis for the rate of change along x-axis. Change in y by change in x. Okay, next. Derivative. D by dx or derivative of x raised to the power n is given as n into x raised to the power n minus 1. And say you have a function like this, x raised to the power 4. Do you know what? One more very important equation that we need to remember is y is equal to f of x. If y is equal to f of x, then either you represent it in this way that f of x is equal to x raised to the power 4 or y is equal to x raised to the power 4. So if you want to find the derivative, either you write it in this way, d by dx of x raised to the power 4, or you write it as f prime of x or y prime. All these three mean the same. And how do you write this? If it's x raised to the power n, it is n into x raised to the power n minus 1. So it is 4 into x raised to the power n is 4. So it is 4 minus 1, which is 3. 4x raised to the power 3. So you have f prime of x, which is 4 into x raised to the power 3. If you have y is equal to f of x, y is equal to x raised to the power 8. Yep. Can you all tell me on what will be the derivative? Either you write it as y prime or f prime of x or d by dx of x raised to the power 8. All mean the same, or dy by dx. Yeah, what will be the derivative of this, dear faculty members? Please, can you respond? I shall wait to see your responses. Wonderful. A lot of you all have already started responding. Amazing. Yep, you're right. A lot of you all have got it right. That it's like this, x raised to the power 8, which is nothing but n is 8 into x raised to the power n minus 1 is like 8 minus 1, which is 7. So it's nothing but 8 into x raised to the power 7. This is your derivative. It can also be written as y prime, as I've told you. So it's 8 into x raised to the power 7. And then we have something called as constant multiple rule. Okay, you have something called as constant multiple rule, wherein d by dx of cu is written as c into du by dx. C is constant. Okay. And if you have d by dx of c x raised to the power n, you take the c out. So this part can be written as, you take c out, it's constant, c into d by dx of x raised to the power n. And x raised to the power n is given here, that it is the c into, derivative of this will be n into x raised to the power n minus 1. And you write it in this way. D by dx of 7x raised to the power 5 is equal to, you take out 7 into d by dx of x raised to the power 5 is 5 into x raised to the power 4, which is 35 into x raised to the power 4. You also have a summation rule. Say you have an equation like this. Y is equal to x raised to the power 4 plus 12x. This 12x that you're seeing is like this. C into u, 12x, right? Oh, this part I think we missed out, my bad. So yeah, 7 we took out, and this, sorry, let me solve this in a detailed manner. So you write it as 7 into d by dx of x raised to the power 5. X raised to the power 5 is written as here. So n is 5. 5 into x raised to the power 5 minus 1 is 4. So 7 into derivative of this is 5 into x raised to the power 4. This is 35. Then we have summation rule, which is x raised to the power 5 plus 12x. Whenever you have a derivative like this, yeah, let me first open up That's for the forum. Can you all please respond on what would be the answer? Either you represent this as y prime or f prime of x or d by dx of this equation y. Why do you write it this way? Because y is equal to f of x. Yeah, please go for it, friends. I mean, there's nothing wrong if you get wrong. If you don't try, then that is wrong. So that's okay. Go for it, please. Okay, so let me write it. This can be written as d by dx of x raised to the power 4 plus d by dx of 12x. D by dx of x raised to the power 4 is written as 4 into x raised to the power, how do you write it? X raised to the power n is equal to n into x raised to the power n minus 1. N is 4, so 4 into x raised to the power 4 minus 1 is 3. Plus, this is written as this component 12 into d by dx of x. This is like x raised to the power 1. So it's 12 into x raised to the power n 1 means 1 into x raised to the power 1 minus 1. This is 0. So 1 into 1 is 1. So it will become 12 into 1, which will be 12. Okay, so you have y prime. Then you have a difference rule. D by dx of u minus v. Yep. Can you all go for this? Please tell me what would be the answer for this. Let me see how many of y'all will get it right. Yep. Go for it, friends. I mean, people, come on, respond. I request everyone to please respond to the different color. Okay, so how do you write this? It'll be d by dx of x raised to the power 4 minus y minus, because you have a minus sign, d by dx of 2x square plus d by dx of 2. This is like x raised to the power n. So it'll be 4 into x raised to the power n minus 1 is 3 minus. You take out 2. 2 is constant. So it'll be 2 into x raised to the power 2. When you find the derivative, you get 2x. Right? X raised to the power n is equal to n into x raised to the power n minus 1. X square is 2 into x raised to the power 2 minus 1, which is 1. Plus constant. What did we discuss? Derivative of a single number is undefined, 0, right? So derivative of a constant would be 0 actually. You get this. 4x cubed minus 4x. Remember, derivative of a constant is 0. Next, let us see how to practically solve it. While I was working with a specific European country, it was a country in, you know, there is something called as Baltic, Nordics and Baltic, right? Like Norway, Sweden, Denmark, Estonia, Lithuania, Latvia, all these other countries which form, Nordics and Baltics basically. And there you do not have any ocean, right? It's a landlocked country. And in that landlocked country, what happens is I can show you an image so that you get a sense of that. Norway. Um, yeah, it'll be like this. Okay, it'll be like this basically. And what happens is these mountain rocks roll and then they fall into this water. And you know what? When the mountain rock falls into the water, the impact is equivalent to a tsunami. It'll be like a tsunami. Everything is washed off. And people, what they have done is on those mountain cliffs, etc., they put a lot of industrial IoT sensors, which will track the movement of the rocks so as to predict on which rock will fall. What is the size of the rock which is going to fall? Upfront predicting that. If you can upfront predict, the advantage is that you can predict on how much time does it take for the circular ripples to, you know, completely probably fill the region basically, right? So, for example, if something falls in the river like this, there'll be circular ripples like this, circular ripples. And all the household nearby, they will get swamped with the water. So it really makes sense to predict on what is the speed at which these circular ripples increase. It really makes sense. So if you have a radius of r centimeters of a particular circular ripple, and if it is related to time t in seconds, and you have a formula of radius, so let's find out. How fast is the area of the circle growing when the radius is 11 centimeters? So if a rock falls into water, what will be the ripple, circular ripple, and what is the speed at which it grows? How much time do we have to evacuate the people? All these analysis can be done. It's done by the natural disaster, recovery team basically. That's why I was saying, right? It's not about just analyzing images. That's trivial. It's all about how do you analyze all these kind of practical things. Okay, so here it's given that r is 4t plus 3, which implies and then if radius equal to 11 centimeters, t will be 2. And area of the circular ripple, area of circle, you all know it's pi r square. So you put pi r square. R is this 4t plus 3 whole square. When you solve it, you get so much. Now, what do you want to know? You want to know the rate at which things are changing. Rate of change. What is rate of change also called as? Derivative or gradient or slope all mean the same. So hence I'm taking a derivative with respect to t and I get this. And since we got t equal to 2, when I substitute that, I get 88 pi. Okay, and when you solve it, you get so much. So when the radius is 11 centimeters, what is the speed at which your area is increasing? 276.5 centimeters square per second. That is the speed at which the waves are moving, and then we need to quickly evacuate the people. This is a practical application of learning derivatives. How is it going to be helpful for us in deep learning, right? So that for that you'll have to still wait. We'll get there. Before that, there are a couple of other things that we need to discuss. If you have d by dx of uv, then you write it as u into dv by dx plus v into du by dx. And say you have this kind of an equation. This is u and this is v. So you have u into dv by dx plus v into du by dx. So how do you write it? U is this x squared plus 3 into derivative of this dv by dx, which will be d by dx of 2x cube plus 5x plus v into v is this 2x cube plus 5x into du by dx, derivative of this. So it will be d by dx of x squared plus 3. What do you get when you solve it? It is x squared plus 3 into d by dx of 2x cube will be 2 into 2 is constant, you bring it out. X cube will be x raised to the power n kind of. So it will be 2 into 3x squared plus you bring out 5 constant into x raised to the power 1. So if you find the derivative of that, you get 1. So it's 5. So it'll be 2 into 3 will be 6. So I'll write it as 6x squared plus 5 plus 2x cube plus 5x into derivative of x square is 2x. Derivative of 3 is 1. So you have 2x. And you solve it basically. So you get an equation and you solve it to get this. Take out a minute and just try to look at this on what we have just done. And there is a last rule which is called as quotient rule. And when it comes to this quotient rule, here is an example. So you start treating this as u and this as v. You write this as v into v is what? X squared plus 3 into du by dx. So derivative of this. So it'll be d by dx of 2x cube plus 5x minus u. U is this numerator, which is 2x cube plus 5x into d by dx of v, dv by dx, right? d by dx of v. V is this x squared plus 3 divided by v square. V is x squared plus 3 whole square. Okay, you solve this and then you can find out the answer. And by now you are aware of how to solve this, right? So this d by dx of 2x cube plus 5x. This is like u plus v. So you solve it as d by dx of 2x cube plus d by dx of 5x. So this will be written as 2, you take it out, 2 into d by dx of x cube will be 3x square plus d by dx of 5x would be 5 into d by dx of x will be 1. Why? Because it's like x raised to the power n, which is n into x raised to the power n minus 1. And if you have only x, it's something like x raised to the power 1, which is 1 into x raised to the power 1 minus 1. 1 minus 1 is 0. So 1 into x raised to the power 0 is 1. So 1 into 1 is 1. So directly I'm writing it. So this is nothing but 6x squared plus 5. And if you find the derivative of this, d by dx of this, d by dx of x squared plus 3 is equal to d by dx of x squared plus d by dx of 3. Derivative of a constant is 0. Derivative of this will be, it's like x raised to the power n. So it'll be 2x. So we'll get 2x here. So it's simply put be x squared plus 3 into 6x squared plus 5. Where am I getting that from? Derivative of this is so much. Minus 2x cubed plus 5x into derivative of this is 2x divided by x squared plus 3 whole square. That's how you solve it. Okay, done. Now, enough of basics. All that we have discussed until now is pure basics. And we have also looked at practically how do you use that. Now, we use this derivative in a broader context, wherein you try to find whether you have a minima or a maxima. Let me give you a couple of examples here. Your, say, we are doing a project for Coca-Cola for that case, right? Let me give that example. The plant head of Coca-Cola might say that, can you help me understand on what is the maximum number of bottles that I can manufacture, PET bottles? Okay, what will be the maximum yield that I can achieve? And when you want to look at the maximum yield, you have to look at various aspects such as number of human resources who are working, number of machines that are manufacturing Coke, and various other aspects. Given these constraints, limitations, what will be my maximum yield? This might be a question which plant head from Coca-Cola might ask us. How do I answer that? For that, we need to look at uh, the subsequent 2 or 3 slides, which will answer this question. Okay. Another question is, can you help me minimize the number of defective circuit boards? We have done a project for a client in Malaysia without naming that. It's one of the gold standard in the space of semiconductor manufacturing. It's a manufacturing plant. What they were doing is that there is this assembly line on which each and every circuit is manufactured. Circuit that you see in your laptop or desktop or in your mobile, there'll be a circuit, motherboard kind of. So those circuits are manufactured. And people stand here. Okay, people stand here. Okay, and what they do is, as in how the circuits are manufactured and as in how the circuits pass through, they inspected manually. They were inspecting manually. Then what we have done is, we have placed a high-end camera here. This camera used to capture the image. So let me put it here. This was more or less like a multispectral camera. Multispectral cam. What is multispectral camera? Please Google that out. Yeah. So there is something called as multispectral camera, which will capture not just the visible spectrum, but also invisible spectrum. Anyways, the moment those images are captured, those images are processed, and we do an image, we applied an image processing algorithm there, which will identify whether this circuit is defective or not, defective or not defective. So there, their goal or objective was to minimize the number of defective circuits. So we have applied this, AI application here, which actually countered and minimized the defective circuits to a great extent. But the question they asked was, all right, you implemented this. What is the maximum benefit that I can achieve? Earlier, without this application, say the defective percentage of circuits was 3%. 3% circuits were defective. I mean, uh, defective, and people have identified that it is defective. Or let me put it this way, I think, okay, better let me put it this way. So what happens is, you know what? After the circuits are manufactured, people inspect it. Your quality assurance department will inspect that. And once they feel it's good, they ship it to the customer. If customer finds some defective, what will the customer do? Customer will return the product. And also customer would be unhappy, right? So you'll return. Since you're going to return, that number of products or number of circuits that are returned should be tracked. And that percentage was 3%. Through your AI application, to what extent were you able to reduce the number of defective circuits? Right? So we have done optimization technique, and we figured out that given the number of circuits that are manufactured per second, right, and various other parameters we looked at, and then we figured out that it was around 0.8% or something. That's the maximum benefit that we can achieve. It cannot be actually made zero, but yeah, that's a significant improvement. For these kind of problems that you solve, you need to have knowledge about derivatives, right, optimization, and you should be able to figure out minima and maxima. So let's understand that now. If you have an equation, see, any business problem, remember one thing, you'll have to formulate it as mathematical formula problem. Any business problem should be formulated as a mathematical problem. So what do? Say there is a specific equation wherein, as and how you keep increasing the x value, say the value along the y direction, okay, keeps on increasing, keeps on increasing, keeps on increasing, keeps on increasing. After a certain point, it will start decreasing. Okay, after a certain point, it starts decreasing. The point where it stops and starts decreasing, this point here is called as maxima. This point is called as maxima. Okay. And say you have yet another equation altogether, wherein you have x value here, and then you have y value here. As and how the value on the x changes, your y value keeps on decreasing, keeps on decreasing, keeps on decreasing. And after a certain point, it starts increasing. And this point is called as minima. Now we need to understand more here, right, about maxima and minima. Let me explain. Okay. Say you have some function, okay, then you have a slope like this for line A, and then you have another line B like this. Will slope A have more slope, or line B have more slope? Will line A have more slope or line B have more slope? Okay, let me ask this question here. So I will put a poll question here for you guys. Which line has more slope? Line A, or would it be line B? Yeah. Please, can you answer this? Will line A have more slope or line B? Let me see how many of y'all will get it right. Which line will have more slope? Obviously line A, right? More slope. I mean, this is steeper, right? You'll come down faster. If you stand here on A, you come down faster, more slope. B has less slope. Next. How about line C? If I have a line called C, and if this is parallel to this line, if this line C is parallel to x-axis, what will be the slope of line C? What shall I say will be the slope of line C, friends? Will line C have a slope? If yes, what would that slope be? Line C will have a slope which will be 0. Right? Line C will have a slope which will be 0 because there is no slope at all here. It's vertical, sorry, it's horizontal or parallel to x-axis. So any place where there is no change, that means as and how you keep changing along x-axis, if you keep changing x value, y value is remaining the same, it's not changing. As and how you keep changing the x value, y value is remaining the same, that is not changing. That means the slope is 0. There is no change. I've already told you that rate of change is also called as derivative or slope, or this is also called as gradient. So if there is no change, as in how you keep changing x, y value is not changing, it's the same. So slope will be 0, rate of change will be 0. If the rate of change is 0, here you'll have rate of change 0. Here also the rate of change will be 0. So rate of change will be 0. Here also rate of change will be 0. Okay, here also rate of change will be 0. Here also rate of change will be 0. But which one is minima, which one is maxima, we really don't know, right? How do I find out? Here, of course, I have drawn that, so you know, but ideally, how do you find out? That's the point that we will solve here. So if you have an equation called y is equal to minus x square, okay, and if you find the derivative of that, you get minus 2x. Derivative of that. Why am I equating it to 0? Because I want to find out this or this where rate of change is 0. Here and here, rate of change is 0. Since the rate of change is 0, what am I doing? I'm finding the rate of change of this equation and I'm equating it to 0. So you get minus 2x. Okay, you equated it to 0. And when you say uh, this implies x equal to 0 basically. Yeah, sorry, just give me a minute. Sorry. So sorry, just give me a minute. Yeah, sorry about that, friends. Okay, so you have a critical value, which is 0. That is what we got here. Now, say there is altogether a different equation y is equal to x squared. When you find the derivative of that, you get 2x. Why are you equating it to 0? Because critical point is that point where slope will be 0. Critical value. Here also slope will be 0. This is critical value. Hence, what you're doing is you're finding the rate of change at this point and you're equating it to 0. Here also, there is a different equation altogether. You find the derivative and you get value 0. Okay, so two different equations are getting the same critical value. Now, the point is this critical value minima or maxima? Right? Is this critical value minima or maxima? This is what we want to find out. To find out whether these two values are, or this value is minima or maxima, is this value minima or maxima, people do second derivative test. Second derivative test. What is this second derivative test? Second derivative test is, this is the first derivative value and um, just a moment. This is the first derivative test. If you find the derivative of this once again, first derivative has given you this. If you find the derivative of this once again, it will be written as d square y by dx square. The derivative of this will be minus 2. If you get a value which is negative, if this gives you a negative value, which implies that critical value is maxima. Okay, that means it'll be like this, maxima. And here, if you take this and do a second derivative test on this, which is nothing but d square y by dx square, you get 2. If you get a second derivative value, which is positive, that implies that critical value here is minima. You have minima here. So you have maxima and you have minima. Okay, so very simple. Take the first derivative, equate it to 0 to get a critical value, and find the second derivative of it, which is nothing but d square y by dx square. If you get a value which is negative, that means it is maxima. The other way around, it's maxima. For any equation, it's the same. Find the first derivative, equate it to 0, and then get a critical value. Is this critical value minima or maxima? How do you find out? You find the second derivative. Second derivative would be 2. If this is positive, you get a minima. That's it. That is how you find out whether something is minima or maxima. And that's what is given here. Okay. You find the second derivative, and if it's less than 0, that is negative, critical value is maxima. If the value is positive, greater than 0, critical value is minima. Next. This is what is explained. You take the equation first, find the first derivative, equate it to 0, and you get the critical value. Find the second derivative test to check whether that's a minima or maxima. Okay, say I give you this equation, can you help me find number one, critical value? What do you think will be the critical value of this? Hint is, find the derivative of this equation, equate it to 0. Can you all do it? Please take 2 minutes. Until and unless you put your ink on your paper, pen on paper, you would not be able to solve. Rubber has to meet the road to be able to understand. So please solve it, and please let me know on what is the critical value for this. Yeah, I'll be checking your answers. So please, I request everyone to respond. I request everyone to respond because this is how we learn. Take quick 1 minute and please solve this. Post that, it will be all deep learning, friends. You will understand deep learning like a T if you understand this equation better, or if you understand the mathematical foundation better. And one more word of caution, I'm not getting into the depth. Okay, again, I repeat, it's an 80-hour session that we deliver. We have compressed that into 20 hours. So I have certain limitations in terms of, or constraints, in terms of delivering as much as possible without getting into too much of depth. A lot of y'all are responding. Wonderful. So let me erase this part and let us proceed further. If you find the derivative, first derivative, you get 2x minus 3 equal to 0. And if 2x equal to 3, then x equal to 3 by 2. Simple. If you find the derivative of this, it can be written as g prime of x. Okay, you get 2x for this. For this, you get minus 3, and constant is 0. So you get 2x minus 3. Why are we equating it to 0? Because slope or rate of change is 0 for critical value. And you get this critical value. Now the question is this critical value minima or maxima? Is this minima or maxima? To find out this, what do? You simply do a second derivative test. What is a second derivative test? You find the derivative of this once again. You take this equation, find the derivative. You get, for 3 it will be 0. For 2x you get 2. G double prime of x, and you get 2. 2 is greater than 0. Friends, first derivative. Here we have first derivative. When you find the first derivative and equate it to 0, what do you get? Critical value. There ends the story. You will not get another critical value here. This is the critical value. Critical value. Is this critical value minima or maxima? Is what we are trying to find out. To determine that, you find the second derivative And second derivative means take this first derivative, find the derivative of that once again, you get a value which is greater than 0. If the second derivative value is greater than 0, then critical value will be minima. Then this is minima. Simple. Let's solve for this also, friends. Let us firm up our understanding in a better way. Can you please solve this? Trust me, after this, your understanding will be very, very clear when we discuss about gradient descent algorithm. You will understand it in a nice manner. So please solve this and let me know on what is the critical value. What is a critical value? First step is you need to find the you need to find the critical value. Okay, quickly, 1 minute, and then I want to see the answer. What are the critical values? Please respond over the chat window. I'm monitoring your responses. I request everyone to please respond. Okay, fine. So what you do is you find the derivative of this. First order derivative. To find the critical value, first what you need to do is you find the first derivative. First derivative is the f prime of x, wherein you get this is like x raised to the power n, right? So you get 3x squared minus this will be 3x because minus 3 into this 2 x squared will become 2x, so it will be minus 6x. 2 is 0, so you get this. Then 3x into x minus 2 equal to 0. When you solve for it, you get two values. You get two critical values, 0 and 2. These are your critical values. Oh yeah, there can be two critical values also. How do you determine whether this is minima or maxima and this is minima or maxima? How do you find out? So here you find the second derivative. Second derivative test. That means you take the first derivative, this, and then find the derivative of this once again. When you find the second derivative, you get 6x minus 6. If you substitute 0 in this equation, you get minus 6, which is less than 0. Okay, hence this critical value x equal to 0 will be what? Minima or maxima? What would this be? What would this be? Minima or maxima? Let me quickly do a poll question otherwise. Or this will be less than, this is less than 0. Less than 0 means critical value will be maxima. Now do one thing. Substitute the next critical value in this derivative, second derivative. You get a number which is greater than 0. If you get a number which is greater than 0, what will be this critical value? Minima or maxima? It will be minima. On one side you have maxima, on another side you have minima. Okay. Fine. So I think we have reached a stage wherein we need to take a quick break. So it's 1 hour time. So let's take a break and let us be back by 6:10 p.m. Until then, we have break. Let's take a break and come back. Okay, so let us proceed further and understand about an algorithm which is called as gradient descent algorithm, which is the de facto for deep learning. Okay, it's the de facto for deep learning, and we will understand it better now. So here, rather than walking you guys through that, let me explain this. What happens here is when it comes to gradient, what is gradient? Gradient is also called as rate of change or derivative or slope. So gradient or rate of change or derivative or slope all mean the same. Again, this is the rate of change. So um, yeah. So rather than walk you guys through this, let me explain here. Yeah. So what happens is our objective when it comes to gradient descent. What is the objective? I'll give you example of a single weight. In the equation that you get to do the prediction, this is how it looks. B plus W1 x1 plus W2 x2, so on and so forth. Or let me do one thing. I think it would be slightly difficult for you all to understand this if I do not explain about first. Let me explain you about deep learning primer, and then you will understand better. So let me go to deep learning primer. After this deep learning primer, where is that? Yep, sure. So you'll understand now in a much better manner. Let's switch from black and white to color. Okay, deep learning primer. We are going to discuss about a lot of things as part of deep learning primer, and this is going to set the tone for our first algorithm. People got inspired by biological system like human brain, and your mathematicians and statisticians thought that if we can have an algorithm which has a similar structure as that of a human brain, then it would start behaving like a human brain. That is what people thought. So you have a biological system and you have an artificial system. If you have a system, or if you can come up with an algorithm similar to this, then it will start behaving like a human brain. That is what people thought. This is how the human brain looks like. I'm sure you know. More the number of folds, people say that IQ level is slightly higher. Okay, but nonetheless, nothing can replace the hard work. The basic unit of information processing is called as neuron. Number of neurons that you have in a human brain is typically 10 raised to the power 11. And average number of connections per neuron is 1000 to 10,000. And the communication speed is much slower. It is order of a few milliseconds. The communication speed is much slower. It is order of a few milliseconds. That means within milliseconds you respond as a human brain. Any complex perpetual task would take just a few hundred milliseconds, just a few hundred. That is called as 100-step rule. 100-step rule means by the time you reach the 100 neurons, basically, you accomplish the task. So the max that you make use of for a perpetual, that is routine task, is 100 neurons. Okay. Now, another thing that you should be aware of when it comes to neural network is that when you supply your image to your neural network, it passes through multiple layers. The initial layers that you have would capture something called as low level features. Low level features means probably there is an edge here. Okay, there is another edge here. Those kind of edges can be identified. Some kind of, and then when you move to the next level, you capture mid level features, meaning probably the circle, the mesh basically here, so on and so forth. When you go to the next level, which is the high level features, it exactly identifies the parts of the car. And then it says that, okay, this is a car. This process is called as compositionality. Uh-oh, just a moment. Let me see here. Not getting audio? Strange. Let me ask this question here. Let me reset and ask. Are you all not able to hear me? Are you all able to hear me? Yes or a no? Please, can you all respond? Are you able to hear me, friends? Wonderful, wonderful. Okay, so there might be a pleasant glitch. Say there is artificial intelligence embedded into this also. The moment you all slightly get disengaged, automatically the audio gets switched off. Okay, let's proceed further. So here we have this compositionality in data. Compositionality means the learning happens in bits and pieces. First, it learns the low level features. It means your neural network, then the mid level features, then the high level features, and then finally you get your output. It's similar to a human face. We have built a face recognition system, by the way. Okay, and you'd certainly benefit from that. Again, I think there will be a glitch. I'm not sure why there is a glitch here. Just give me a minute. Let me check, quickly do the speed test. Wonderful, this is working well. It's worth testing quickly. Okay, speed is fine. Yeah, please hold on with that attendance thing, right? We will give you the link. Just let's focus on this. So if you have images, image of a person, for example, if you pass the image of a person as an input, the initial layers will capture the edges. So if this is the face of the person has edges, this is an edge, this is an edge, eye is an edge, nose has an edge, mouth has an edge, ear has an edge, so on and so forth. All those edges are captured. Okay, and then the next layer. So this is the initial layer. So the initial layer captures what kind of information? Low level information. And the next layer will capture mid-level features like nose, eye, ear, so on and so forth. And the next would be high-level features. High-level features would be face of a person, so on and so forth. And then it would classify on whether that's a human or not. It's like automatic attendance tracking system. It will track the attendance, right? All the employees of your office, if you take their images and train your model, it would start predicting on who is that person who has entered the office premise. Okay, so if you have an image, from the image you can do a manual extraction of the features. Manual feature extraction. Features means inputs, right? Basically, simply put, features means inputs. So you'll have all those inputs. You can manually extract the features using something called as, shift invariant feature transform or histogram of Gaussians, etc. You manually get the features and process them. Or say you have speech, you use MEL frequency Separable coefficient and extract the features. Or if you have textual data, you use some kind of parse tree, syntactic, etc. to get the data. And you use that data for further analysis. But when it comes to your deep learning or neural network algorithms, these kind of features are automatically extracted. The features are automatically extracted. So shallow machine learning models will, you'll have to handcraft the features. You have to manually extract the features. Those features which are extracted can be supplied to your classifier, which would then classify on whether it's a car or a bus, etc. And on another side, you have deep learning models. What happens in deep learning models? It will automatically extract the features. So you automatically extract the features. Okay, here in shallow, you manually extract. Here you automatically extract the features. Now we will spend some time here to understand about the neuron. Very important for us, right? This is called as a neuron. And when it comes to neural network, depending on the number of inputs that you have, say you have a data set, okay, and you want to predict something, and say you have multiple inputs, 1, 2, 3, 4, 5 inputs, 1, 2, 3, 4, and 5. So you have x1, x2, x3, x4, and x5. Okay, so you have 5 inputs. If you have 5 inputs here, you'll have 5 neurons in your input layer. This layer that you're seeing is called as input layer. Okay, this is called as input layer. In this input layer, you have 5 neurons because you have 5 here. And what is this another additional input that you're seeing here? This is called as bias. Let me explain. If I draw like this, and then say I have, or we have another class like this, you have pink crosses and blue circles. You segregate these two classes using a line. You draw a line and segregate these two classes. And what is the equation of line? Y is equal to mx plus b, or you can write it as b plus mx. On similar lines, you have y is equal to b plus wx. I can write in this way also. This is the equation for neural network. Basically, this is the equation of line, same thing. Now, you have the b here. That's the b you have here. You have W, that's the W that you have here, into X. And this B is multiplied by 1, hence you have B here. So the input that is supplied here is always 1. 1 into B is B. And you have the various other things. So how do you, I mean, the reason why we have B and why we have 1 here is this reason, because this is always multiplied with 1. 1 into B is B. This is bias basically. Now, okay, so you have your equation input layer basically, right? So we have the input layer. Now these inputs have some weights associated, and all these weights that you are seeing here are automatically assigned, randomly assigned. These weights that you see are randomly assigned. Now, and then there is an integration which happens. Two things. Whenever you have a neuron contains two components. What are the two components? One component is called as integration component. Another is called as activation component. So you'll have two components, integration component and activation component. Integration component is always given using sigma. I mean, you can have other integrations also. Sigma is most widely used. Sigma means summation. So what we are doing here is you are having all these weights randomly assigned. Okay, all these weights are randomly assigned basically. And when you do a summation, it'll be like this. B into 1 is B plus W1 into X1 plus W2 into X2 plus W3 into X3 plus W4 into X4 plus W5 into X5. You'll get such an equation. All these will be numbers. All these B is called as bias. All these W's that you see are called as weights. B is bias and W's are weights. Okay, now, and that's a summation basically. You have the summation. And then you get a number here, right? When you solve it, all these are numbers. When you solve it, you get a number. Say you get a number which is 0.8. Just as an example, say you got 0.8, hypothetical example. You pass this 0.8, which is this integration value, into your activation component. Say here you're using some activation function which is called a step function. You can use many, but assume for now that there is something called as step function, and assume that we are using this step function. Assume that we are using step function. What does the step function do? It works like this. If this value, that is the integration value, whatever is this integration value, right? If this value is greater than 1, or I would say greater than 0, it implies that output will be equal to 1. If this is greater than 0, output will be 1. If this value that you get is less than or equal to 0, then say output will be 0. Here you have output, right? So say this output is 0, 1, 1, 0 in that way. 0 means patient has cancer. Assume 0 means patient does not have any cancer, no cancer. Okay, I repeat. Number of inputs that you have will be number of neurons in the input layer, and all those inputs will get attached to the neuron in the forward layer, and all these weights are randomly initialized. All these weights that you're seeing here, all these weights are randomly initialized or randomly um, initialized, meaning all these are random weights. And after that, these weights will get updated. That's a different story. But initially, all these weights are random. You take all those random weights and sum them up. That's the integration part, integration component. And once you integrate it, supply the value to the activation component. If the activation component is step function, then this is how it works. If this value that you get, or the integration value that you get, if this is say 0.8, then 0.8 is greater than 0, so the output will be 1, means cancer. If this value here is less than or equal to 0, then the output is 0. That means no cancer. Okay, so that is how you get an output. So you have two components. One is integration, another is activation. And you have the input layer and you have the output layer. Next thing. Now what happens here is, since initially the weights are randomly assigned, okay, and say here you predicted, your model predicted that patient has cancer, 1. But actual data says patient doesn't have cancer when you compare. That means there is an error. With that error, your algorithm will come back and update the weights. Here is where your gradient descent algorithm kicks in. Gradient is rate of change. Gradient means rate of change. Descent means downward direction algorithm. So you first go forward, calculate the error, and here your objective is to minimize the error. So you go forward, calculate the error, and come back and update the weights. Error, or rather I will put it as loss function or cost function, right? That will be better. And you come back and update your weights. So initially, how are these weights assigned? Randomly, right? So let me pick one weight. Okay, let me pick only one weight, probably W1. And when this weight is assigned, you get some cost or error, right? And error surface will look like this. Okay, it will look like this. Like that, okay? And what happens is, say you assign your weights and your weights were randomly assigned here. It need not be always at the start. Somewhere here also your weights might get initialized. We don't know if I were to extend this. Okay. So here your weights got initialized and this is your error. So when you back propagate and update your weights, your objective should be to minimize your error. So again, you update your weights. Okay, when you update your weights, your error reduces. After you get the updated weights, again move forward, calculate the cost, and again come back and update the weights. So again, you're updating the weights. Why are you updating the weights? With the intention to reduce your error. Again, go forward, calculate if there is any error. Again, come back and update your weights. Again, update the weights. And after a certain point, when you update the weights, your error starts increasing. So you stop at a point where your error starts increasing. You stop and say that, okay, these are the set of weights for which I'm going to have the minimum error. This is called as minimization problem, optimization, minimization problem. And this is called as minima. This is yet another minima. This is another minima. This is another minima. This is another minima. All these are minimas. Out of all these minimum values, out of all these minimum values, the value which is the least is called as global minima, probably this, right? Out of all these minima, say this is the least minima, least error. This is called as global minima. And the minima which is not the global minima is called as local minima. So you have global minima and you have local minima. Okay, this is another thing that you need to remember. And since you are going, gradient is rate of change along the downward direction, descent. Hence it is called as gradient descent algorithm, because rate of change along the downward directions, descent. It's not, that's why it is not called as gradient ascent, it's called as gradient descent. So you're moving downwards. Is it guaranteed to reach a global minima? No, it is not guaranteed. Why? Because the weights are randomly initialized. You only hope that I am going to initialize the weights multiple times. So I keep initializing. Sometimes I might initialize here and I might reach this minima. Sometimes weights might get randomly initialized here and it might reach here. Sometimes weights might randomly get initialized here and you might reach here. If you're lucky, it might randomly get initialized here and then you would reach the global minima. If you're lucky, that's very, 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 very rare. I would say next to impossible. I would not say impossible, but I would say next to impossible. And this process of moving forward and coming back to update the weights, okay, is called as back propagation algorithm. Back propagation algorithm. This is back propagation algorithm, but then when you go forward and come back and update the weights, it's back propagation, but reducing the error is part of your gradient descent algorithm. It will keep reducing the error. These components that we just discussed is very, very important. It is all fine. Now let's discuss about how the weights are updated using Rosenblatt. That's what is used heavily, right? This is the formula that we'll be heavily using. But what is that formula? We will understand using this example. Say you have 4 data points wherein you have z equal to 1, red class, and z equal to 0, you have the blue class. And your objective is to build a classifier. Classifier means draw a line and say that anything which falls here is red, anything which falls here is blue. Okay, that's your objective. Now let's understand. Say you have randomly initialized the weights, and what is the formula to update the weights? Formula to update the weights is new weights is equal to old weight plus eta value. This is called as eta or learning rate. And this eta or learning rate value ranges from 0 to 1 into error. Error is nothing but true value or actual value minus predicted value into input. This eta value is empirical in nature. That means you as an AI expert decide on what should be the learning rate. I'll tell you the advantages and disadvantages. Say you have an error surface like that. Okay. Say your weights randomly got initialized here and you have a corresponding error. If you have a learning rate value which is very large, close to 1, what happens is if this is the minima, it might skip and go here. So it might overshoot the minima. When will that happen? If your learning rate is very high. If your learning rate is very small, then what happens is it will take infinite steps. It will take infinite steps, too many steps to reach the minima. It will be very, very time consuming. So choosing an appropriate eta value is appropriate. It is the need of the hour, or if you want your algorithm to work well, then you need a proper eta value. So let's apply this formula, and the formula is also given here, new weight equal to old weight. Say your weights were randomly initialized as 0 and 1. You have chosen an eta value as 1 by 3. If your weights are randomly initialized as 0 and 1, say you have one value which is throwing an error. That means it is above. Anything above this line should be red. So this will be right classification. This will be right classification. Anything below should be blue. This is also correct. But here this is not, this should have been below the line. It's above. So it'd be misclassified as red as z equal to 1. Ideally it is z equal to 0. So for this misclassified entry, we need to update our weights. For this misclassified entry, you need to update the weights. So this will have two inputs, -1, comma 0.5. 0.5. So new weights is equal to old weight. Old weight is 0. 0 plus eta value is what? 1 by 3. 1 by 3 into actual value minus predicted value. Actually, this is 0. Blue color, 0. But it has been predicted that this is 1 because it's falling above. So 0 minus 1 is nothing but -1. That's your error. Into input. Input is -1. So you have -1 there. And you get some value number. Then this part is updated. Now we need to update this part, which is 0.5, right? So new weight is equal to old weight, which is 1 plus eta value, which is 1 by 3. So you put 1 by 3 into error. Error is what? 0 minus 1. It is uh, actually it is 0, but it has been predicted as it is 1 or classified as 1. So 0 minus 1 is minus 1 into 1 by 2. This 0.5 is nothing but 1 by 2. When you solve it, you get 5 by 6. So these are your new weights. Once you get the new weights, you once again plot the classifier. This time the classifier has still misclassified this. So this has been misclassified. So again, you need to update the weights. And the formula to update the weights is old weights is equal to new weight plus eta learning rate into true value minus predicted value into input. This TI is called as true value, actual value, all of that. So we are getting started with these weights, okay? And this is misclassified. So it's 1 by 3 plus eta, which is 1 by 3 into true value minus predicted value. In reality, it is what? 0, blue class. But it is falling above the line, so it will be predicted as or classified as 1. And 0 minus 1 is minus 1. So you have minus 1. Into input. The input for this is minus 1, comma 0.5. That's two inputs, minus 1 and 0.5 into minus 1. You get a new weight. But for this axis also you need that weight. This also should be updated. So new weight is equal to old weight, which is 5 by 6 plus eta value, which is 1 by 3 into actual value minus predicted value, which will give you minus 1 into this 0.5 is nothing but 1 by 2. And when you solve this, you get 2 by 3. So you get 2 by 3. These are the new weights now. Take these new weights and now again you plot it. This time there is no misclassification. So your classifier, this line, which is called as classifier, updated the weights accordingly. Okay, so again, let me do a quick recap. So what happens is, if you have, say, 4 inputs, then how many neurons will you have? 4 neurons in your input layer. Let me take a data set, just a hypothetical example. Okay, say you have an output variable and 4 inputs, 1, 2, 3 and 4. So you have an output and you have 1, 2, 3, 4 inputs. Okay, and this is x1, this is x2, this is x3 and this is x4. You have 4 inputs and you have one output, right? So all these will connect to a neuron. This neuron will have 2 components. Integration component. Integration can be summation or anything else, but by default it is summation. And then you'll have activation function. All these would be connected to this neuron. And in addition to all these inputs, you'll have another input, which will always have 1. This is called as bias. This is W1, W2, W3 and W4. And finally, you'll get an output. These weights are initially, how are these weights assigned? Randomly these weights are assigned. Okay, randomly these weights are assigned. And you go forward in your network, you calculate the predicted value and then take the actual value also. So what you do is basically you take all these inputs, say age, gender, income, so on and so forth. Take those, pass it through your network. And when you pass it through your network, you'll get the predicted value. Compare that with this actual value. Okay, and then if there is any error, mismatch, then go back and update your weights. Okay, so you go back and update your weights. This process of coming forward and going back is called as back propagation algorithm. And the process of changing your weights to get to the minimum error. So you'll have error and you'll have weights. This process of, trying to get to the minimum error is called as gradient descent algorithm. Gradient is rate of change. Descent because you want to keep going in the downward direction to reduce the error, because minimum the error, if the error is minimum, that's better, right? So that's called as gradient descent algorithm. This is an optimization algorithm. Okay, so let's move on. These are a few things that you need to just remember. Okay, so you'll have integration function and activation function. You move on. But the biggest problem here is that this algorithm that we have just discussed, right, handles only linearly separable boundaries. So if you have your data set like this, wherein you have red, black cross and pink circles, and if you want to segregate these two classes, you just draw a line like that. That's called as classifier. This line is called as classifier, which will classify these two classes into pink circles and black crosses. If you have a non-linear boundary, for example, if you have like this, and if you have the crosses, then to segregate these two, all you do is draw a line like that, like that, like that, like that. Right? So using a single line, you cannot. You need multiple lines. So if you look at the algorithm that we have discussed until now, which is called as Perceptron algorithm, what happens is you'll have your input layer and an output layer, and you connect it in this way. And then you have this neuron, which is segregated into two components, integration and activation. This is called as Perceptron algorithm. Perceptron algorithm just has one output, input and output. That's it, nothing else. But when it comes to your this setting, which is called as non-linear pattern, and this is called as linear pattern, by the way. This is linear pattern. This is non-linear pattern. And this nonlinear pattern can be captured by making use of multi-layered perceptrons. This is perceptron. Multi-layered perceptron, if you can use, then if you can have multiple lines like that, you can capture the pattern and say that anything falling inside is pink circle and anything which is falling outside is black cross. So for that, this is how it will be. So you'll have your input layer and you'll have your hidden layer and you'll have your output layer. And every neuron will be connected to every other neuron in the forward layer. These are your inputs. Say you have three inputs, x1, x2, x3. Of course, you'll have one bias, always one. And then these are the hidden neurons, h1, h2. And then you have your output. We are going to build on top of this. And we are going to discuss about what is multi-layered perceptron, how the weights are updated, how many hidden layers can we have, how many hidden neurons can we have, how do we mathematically update the weights, right? What do you mean by gradient descent, batch gradient descent, stochastic gradient descent, mini batch gradient descent, algorithms? What do you mean by iteration? What do you mean by epoch? We will learn about all of those things on Monday, right? Monday we have the class. Enjoy your weekend, and on Monday we shall have a class. And no, perceptron algorithm is different. Back propagation is just used to go back and forward and update the weights. Gradient descent algorithm is used to minimize your error. Optimization is used to maximize or minimize. Back propagation is used to update the weights. Yeah, hope that answers your question. All right, quickly, do you know what? In order to watch the recorded videos, please go to 360 digit mg, and when you scroll down completely, you will have this link, which is the YouTube channel. All you need to do is click on that, and you'd be able to see day 5, right? You can watch the video. All the 5 days are there. You just need to subscribe and click on notification. Please, there's a request from my side, if possible from your side, please ask your students and the other faculty members to subscribe and click on notification so that they also learn a lot of things. Another thing is, please click on this LinkedIn and please follow our page, and there'll be questions posted. Wonderful. Day 5 quiz is already posted, so it's all yours. Please answer to this day 5 questions in the comment section. Okay. All you need to do is go to 360 digit mg. This is the one-stop solution where you click on LinkedIn. Okay. If you click on Facebook, you'd go to our Facebook page, and I request you all please to follow. Ask your students, ask your faculty members to do the same. And here you have, where did that go? Yeah, here is a quiz, and you can take the quiz. All right. And mind map, if you want to access the mind map, you have a mind map here. Please click on this mind map and do a drop down, select AI and deep learning, and it's all yours. Okay. Click on this and proceed further. Thank you all so much once again for joining in, and we have had a fruitful 1 week is what I'm sensing. Next week we will be delving deep into this, and you'll be learning amazing things about how to handle image, vision, etc. Thank you all so much. And I'm not sure how to post this. Let me copy the link and let me click here. Is there an option to post here? Create a channel to join this. I didn't quite get. Let me see if I can post it. My dear team members, Our team members, sorry, I'm asking. Can you just post on the chat here also the link attendance? But this is not a formal way of taking the attendance. So we actually put the attendance link here. We'll post on the WhatsApp group, by the way, so that it's easier for you to give the attendance if not. Yeah. Thank you all and have a great weekend. Thank you.